Thanks for Barry's introduction. My name is Hsien-Chin Chiu. And now I'm a professor in Chang University. And for the past 5 years, I was engaged by UMC and WebTech to do the 6-inch gallium nitride RF and power devices development. So I co-work with Barry. So today, my presentation, I will base on the device development and the foundry service perspective to introduce you how about the gallium nitride electronic device in Taiwan compound semiconductor ecosystem. Okay, this is my outline. First, I will try to use the gallium arsenide because gallium arsenide is a mature compound business in the worldwide, and Taiwan is very famous for the gallium arsenide foundry service. So what we can learn from the traditional gallium arsenide foundry service history for gallium nitride reference. Then I will introduce you the gallium nitride electronic device application, market, and what opportunity and the challenge for the Taiwan compound semiconductor ecosystem. Okay, this is the compound electronics devices technology timeline. As you may know, for the gallium nitride devices, there are two mainstream applications. First is for power electronics for sure, okay? And another one is the RF electronics for communication. Okay, for example, for the first commercialized power GaN devices was announced by Panasonic in 2005. One after another, EPC 100-volt E-mode HEMT, and high voltage cascade gallium nitride HEMT by Transphone, and Navitas monolithic gallium nitride integrated circuit, and eventually 2018, the first you can buy the gallium nitride quick charger in Costco, 2018. So it's almost the go-to high volume production for the gallium nitride power electronics development. As to the microwave device, the first commercialized gallium nitride RF device was proposed by Cree 2005. It was its discrete label, and later on, the gallium nitride on silicon was demonstrated by Nitronics. Now it has been merged by MACOM, and 2008, MMIC, yeah, and 2010. Gallium nitride RF devices try to replace the traditional LD modes for the 4G base station. It means that gallium nitride RF device go to the high volume production, especially for the base station. And later on, around the 2020, the gallium nitride was engaged for the low Earth orbit satellite communication, for the 5G base station maximum architecture, and recently Infineon even put the gallium nitride on silicon for the maximum authority amplifier. So here I'd like to talk about the first, no matter RF or power device, gallium nitride device. Now it's 2025, so there is 20 years development. So just leverage is similar the gallium arsenide business because I also show now in Taiwan we have the mature gallium arsenide device supply chain because as you may know, the first gallium arsenide MOSFET was proposed, was really in practical application in 1980. And year 2000, in Semiconductor, we have the 6-inch pure play function in Taiwan. So it's also take the 20 years. So it means for the 20 years, maybe for technology development, idea maybe quick, maybe have a short circle time because you know the application, you know the fabrication, know you can do the product. But for the 20 years, now the business may be for the cost effective. Foundry service may be a better way for the high volume production and to go to the real applications, okay? So I try to use this slide to catch 3 points. First, 20 years may be good for foundry service. Second, which is the wafer size for gallium nitride power or RF device? Because in Taiwan we have many 8-inch, of course 6-inch, but we have many 8-inch process. And let's consider about the mask layer. The mask layer is around 15 to 20 layers. So it's suitable for the 8-inch process line, especially the GaN for the RF device. For power device, maybe 0.5 is good enough, but for the RF, maybe have to go to the 0.1. So 8-inch fab is also familiar with 0.1 photolithography. So I mean, last point is for the high volume production and the cost effective, you try to separate the business as a AP house and the pure play foundry service instead of the IDM in Taiwan. Okay, here I summarize one table to tell you about the top 4 applications for the power GaN and the RF GaN. And this table was summarized based on 3 perspectives: gross margin, IDM versus foundry ratio, and the compound annual growth rate. Okay, so first I will try to answer one question. What's the influence and the opportunity after TSMC quit the gallium nitride business? But my answer will be the same to the Professor Chang. Why? Because you can check for the gross margin, even for quick charging, no, very, very bloody. Because it's high volume production, especially we have to face the challenge from the raised supply chain. Okay, so but even go to the power supply unit, industrial, or some very, very niche defense or infrastructure IF device, the gross margin about 35, 40. So it means, and for the single business, even go to the 2027, single business still less than $1 billion US. So I mean the market size really smaller to be considered by TSMC, and the gross margin, of course, TSMC can find a good opportunity to catch the higher gross margin product. So that's my answer. Okay, so they will consolidate their resource, and because for gallium nitride, I just tell you 8-inch may be the best scenario. So I mean, for TSMC, they try to consolidate their resource to the 12-inch. Okay, because today we also try to talk about AI, so I use the AI to generate one picture. I separated the Taiwan gallium nitride semiconductor ecosystem as a 6 parts for substrate, AP, foundry, design, package, and module system level. Okay, so of course in Taiwan, we have a very good foundation for the foundry service. We have many high level with high automation, 6-inch and 8-inch fab, and all of this fab was fully depreciated. So a lot of silicon device, they try to do the further cost-effective solution, and they move their 8-inch silicon device to 12-inch. So it means that now the 8-inch fab, they are eager to catch some new opportunity to fulfill their 8-inch product. So gallium nitride on silicon, of course, is a very good solution for 8-inch next generation consideration. Okay, and in Taiwan, we also have a very good and mature power and RF device packaging and high relevance power supply system. Actually, you can check the module and the system level. 2 inside this list, 2 companies was listed in the NVIDIA power supply unit supply chain. Okay. Okay, but for the past 8 years, Taiwan government support, we also have the mature silicon and the silicon carbide supply chain in Taiwan. And of course, we still have a lot of very good MOCVD talent because we have the past 20 years, we have the LED business. So we train a lot of talent for the MOCVD. And we also have a very good pure play AP house and the foundry culture in Taiwan. We can make our customer system level company to trust no matter the AP or foundry service in Taiwan. So, but still try to do something for Taiwan because we try to keep the ecosystem as a profitable closed loop inside Taiwan, but still have the 2 weaknesses between inside this supply chain: AP to foundry and foundry to design. And later I will show you where are the opportunities and the challenges. And of course, it's really wonderful. In Taiwan, we also have some internal supply chain to provide the specific for compound semiconductor, ALD, ALE, or WAN-based company. And we also have some company, they pay a lot of effort to do the dynamic tester for or high-frequency, high-power tester for gallium nitride. And some company, they pay the effort to do the gallium nitride driver IC to make this closed-loop ecosystem more perfect. Okay, as I mentioned about the ecosystem level challenge and opportunity between AP house and the foundry service. Actually, you can check no matter for GaN silicon power or GaN silicon carbide RF device substrate plus AP, more than 50% for the overall cost structure. It means in Taiwan, most of the foundry, we have the in-house AP, but it will consume a lot of fab space, including the MOCVD, metrology, hydrogen safety region, and of course, you don't have any economic scale. How can you negotiate and the bargain with the substrate supplier, you don't have enough economic scale. So it's really a challenge between the AP house and the foundry. But what's the good opportunity for the past 20 years development? Now the AP house, they have enough knowledge and the technology to demonstrate the low dynamic ion AP structure for power, low insertion loss, and low harmonic IF AP structure for IF. Okay, and of course they have maybe 10, 20 MOCVD, so they have enough backup tool and equipment facility for supply chain, and they can have a good bargain power to negotiate the substrate cost to silicon or to silicon carbide. Okay, and now some AP house, they also have the ability to provide you the regrowth, no matter for the ohmic or for the strength enhanced layer service. So there are some good opportunity in Taiwan supply chain, especially for AP house. Let's talk about the challenge between the foundry and the design house. Okay, actually, I would like to say I have always think about it's very successful for silicon foundry service in Taiwan, but the compound foundry service, the platform business model, maybe it's not the best solution for the compound foundry. Why? Because once you have the one platform, but your final product, eventually you have to customize based on the application. Okay, this is a very important difference culture compared to silicon device. And for example, different application for LLC, for PFC, for motor synchronized rectification, motor control, different application, different loss scenario. Different loss scenario, how can you push the further efficiency improvement? No. And you have to, for the design house, you have to translate the system level parameter, especially dynamic parameter, to design. Then you have to negotiate and try to figure out and find out the good solution to improve your device level. Actually, now the interaction between the foundry and the design house, we really have to improve it to make the whole architecture more efficient. Okay, and not for high efficiency power supply unit, for example. Actually, the only effort on device is not good enough. You have to optimize your device and a good driver, PWM driver, to make your whole system more efficient. It's also important. So I mean, it's not an only single business issue. And of course, you want to co-work with driver. For foundry side, you need to provide the PDK. I have to say, for compound semiconductor, I reference one big guy, he said, the model in compound is a fuzzy model. It's fuzzy model. You always have to put the triple model, small model, scalable model. Difficult. But we have to do the effort to provide the good model to our customer. And what's the opportunity? Because the very high relevance customer in Taiwan, so you can find the very good customer support in Taiwan. And we also have many 8-inch and high automation tools in Taiwan. So that's an opportunity between the foundry and the design house. Once you realize the design house and the foundry service, you have to negotiate not only the device level parameter, how about the system level parameter? Okay. This is a single figure to show you that there are two traditional VAC to 48 power supply unit in rack. And considered by totem pole bridges, PFC is belong to the hot switching, and the isolated full bridge LLC is for soft switching. But there are three kinds of the device has been adopted for the AI power supply data center unit. And for a primary side and the secondary side of the LLC is very simple, it's soft switching. So gallium nitride can play a very good role for these two applications, no matter the 650 volt and the 100 volt. Okay, but this is not the case to the AC to DC hot switching. Why? Because you may know for the Navitas and the Infineon, they both have a very good gallium nitride solution, but eventually they still use the GeneSiC and the CoolSiC to be the first AC to DC converter device. Just because for GaN silicon, you still have to face the high temperature. The ion have the performance degradation at high temperature, even more than twice magnitude. So it's very important for PFC, especially for high temperature. You have to face the hard carry effect. So for 650 volt gain nitride, especially for hard switching, it's still gating. Okay, especially many speakers also talk about the next generation announced by NVIDIA. They have to eventually, for the efficiency consideration, the DC voltage will go to 800 volt. Wow, yeah, you can gain the reliability, PSU reliability, less copper usage, and better efficiency and good form factor. But it's given the challenge to the device guy. Okay, so how can we provide a good DC to DC from 800 volt to 48 volt device? There are two scenarios. One is high voltage, one is low voltage. And of course, with very small form factor. And the opportunity maybe point out, the first level, you can use the 8-inch low QG because the frequency need to go to the 100 kHz. So low QG and low COSS 1200 volt silicon carbide MOSFET would be the best choice now. But how about the 8-inch low gauge current 1200 volt GaN on silicon? Is semi-insulating substrate, not the N-type substrate. What's the opportunity? Okay, last year, one vendor in Taiwan, they tell me, hey, now the 6-inch is not the mainstream for silicon carbide substrate. We have the 8-inch supply, silicon carbide supply in Taiwan. I say, wow, what's the price? Oh, I have to thanks the silicon carbide business. Now the pricing have a very good recession for the pricing, and even let's say 8-inch silicon carbide semi-insulating, the pricing. But it's not the prime level, it's only research level. Yeah, less than $1K US. Maybe you don't have any sense to the pricing, but it's very sensitive to me. Wow, less than 1K, and eventually can be lower. So I eventually find that for GaN on silicon, from the GaN nitride to silicon, you have the 18% lattice mismatch, but it's only 3% gallium nitride to silicon carbide mismatch. So it means for the buffer layer thickness, GaN on silicon, if you want to do the 1200 volt, you have to cross the MOCVD more than 5 micron, because for 1 micron gallium nitride, it can offer you the 250 volt. But for silicon carbide, actually the voltage was blocked by the semi-insulated silicon carbide substrate instead of the gallium nitride buffer. So you can just cross a very thin buffer for the gallium nitride AP layer growth. So far we can demonstrate the 8-inch GaN on silicon carbide with ultra thin buffer. And we also measure the 4 kinds of device: GaN on silicon, GaN on 3C silicon carbide on silicon, GaN on silicon carbide 1.5 micron, and GaN on silicon carbide ultra thin barrier. Okay, there are 2 groups. If you really put the GaN on silicon for the high power electronics, okay, you have to suffer the very high slope of the PDC to temperature increase. So if you use the GaN on silicon carbide, you have a very, very small slope for the temperature increase, especially the thin, ultra thin buffer. Actually, the less thermal boundary layer. So eventually, we found that the GaN on silicon carbide can get the very similar thermal dissipation behavior, just like the silicon carbide vertical device, and with a very good AP quality. It's only 0.65 micron, but the quality is totally different group. Okay, so the opportunity of the 1200 volt GaN on silicon carbide HEMT, maybe we don't have to compare the GaN on silicon because I just tell you the thick box and the poor thermal issue. But how about compare the GaN on silicon carbide HEMT to planar silicon carbide MOS? Okay, be honest, based on the phono scattering, actually the semi-insulating silicon carbide can really reach the 400, almost 5 watt meter K per meter, but this value for N-type is only 370, and for AP thickness is less than 1 micron, but for HT-CVD more than 1200 volt, you need to cross by HT-CVD 10 micron silicon carbide. So I just show you the one picture compared to silicon carbide substrate cost. No, similar. For the AP growth, similar. But one key issue happened. Because in Taiwan, GaN on silicon carbide, you can submit the wafer to the Unruly backend foundry service directly. Yeah, because of the gallium nitride. But for silicon carbide, you have to, I referenced one picture from Yo. You needed to purchase the high temperature imprinter, high temperature oxidation, and at least in Taiwan, you needed to pay 3 billion Taiwan dollars to increase some high temperature equipment for the 1200 volt silicon carbide device. But if you eventually use the GaN silicon carbide HEMT technology, you didn't have to increase the high temperature equipment. So let's, and of course, the breakdown voltage, silicon carbide is very good for the breakdown voltage. Actually, the breakdown voltage was dominated by the back end of the night on the gallium nitride surface. Okay, so another opportunity is I just mentioned about it for the EMO 650 volt. The device improvement should depends on the different application, and you have to measure the different power loss and the partition, which is the device getting, and then do the improvement. So this figure I just try to show you for the design house side and the foundry side, you have to discuss about the parameter, but not only the DC parameter. How about the system level parameter? It's a good interconnection. Okay. As to the low voltage GaN on silicon, okay, for the first speaker, Professor Chang also mentioned about, wow, you have to face the same power, but low voltage means the high current. So for the high current device, sometimes more than 100 amp. So for the system level, the only package, you don't want to influence your on-read system from package, so the best solution is still the copper pillar or copper bump. But for the bump, it's very easy, demounted in the high power server. So you may notice the yield for the less secondary side, only 50%. Sometimes you have suffered the bump demand issue. But for our proposed device, we use the TSV for gallium nitride power device, because the backside via is a very regular process in compound foundry, and we just move the drain pad through the TSV to the backside metal, and for the traditional 100 volt gallium nitride device, you have a lot of back end. So means a complicated back end means the very, very, much parasitic effect. But for our device, the drain side is on the backside metal, and the source side, you just can leverage the silicon carbide device, just use the copper clip to do the package. The cost is also considerable, and the front side metal can totally follow the source layout. Okay. And of course, the wafer was slimmed down to the 50 micron. It's very good for thermal dissipation. Okay, now talk about the RF GaN applications. Okay, so far we use the 5G anytime in the real life and through the macro cell. But now in the urban or downtown area, you have to support the wide bandwidth together with the mass user equipment. You have to use the maximum small cell, and but for the maximum small cell and macro cell is only cover the Earth's surface about 10%, only 10%. So the other, the rest of the area, you have to leverage the low Earth epitope to the cruise, to the airborne, and to the emergency. When you travel to some national park, if no base station signal, in emergency case, you have to connect to the satellite directly. Okay, and for the military and the next generation communication will be the 5 trustable Taiwan company industry in the near future. And okay, and this figure I just to show you the different frequency, different power level, different application. But if you cut a red line to the 20 watt, actually, now the GaN silicon carbide for high power satellite or high power military or high power base station, still GaN silicon carbide. But if less than the peak power 20 watt, GaN silicon has been passed the high temperature H-top by some institution. So it's very good for if you have the 8-inch or 6-inch GaN on silicon power device process line. How about the GaN on silicon for RF? Okay, Now the base station is totally different recently. Traditional, I leverage one picture from Mitsubishi. Traditional, the base station will be the remote radio head, and you have to provide the 100 watt power amplifier by using GaN and silicon carbide. Wow, it's full radiation. 100 watt is such high EM wave power. But now, in order to make the system more efficient and more user, now the maximum will become the mainstream. It means that the single high power was separated to the 8x8 or 4x8 active antenna system. Okay, just like the active antenna system base station over there. And when you separate one big power amplifier to the 64 power amplifier, okay, it's very good for the hardware, for the function. Why? Because I can provide you the 64 LNA switch and the PA. Okay. Okay, so now it's the new era of the gold-free 8-inch GaN silicon PA for maximum of base station. Last year, the Infineon announced the GaN silicon for their 8-inch solution. No, so not only the Infineon, GlobalFoundries, XFAB has the 8-inch gold-free GaN HAMD for RF and the power simultaneously. And of course, GaN silicon can for high power switch because of time limitation. P-GaN is not only solution. P-GaN is not only for power. How about for the RF switch? Also doable for the 10 watt base station switch. Okay. And the loss orbital, there are 3 frequencies: KU band, Ka band, and L band for the different applications. And eventually, you have to use the 0.25, 0.15 micron GaN nitride IVO solution, and it can also a good opportunity for the 8-inch GaN silicon foundry surface. Okay, and for the CAT and IMEC, they have the published paper. They use the 8-inch copper back end of the line. So I mean. Not only the gold solution, actually the copper backend of the line can also do very good power amplifier with the past reliability data. And we also have the project with the E3, and we also do the T-shaped gate by using the titanium nitride plug instead of the E-beam lithography. Okay, and a lot of people try to put the GaN nitride on serial phone. Yes, it's possible. It's really possible because the frequency was pushed to the FR3. The frequency go to the 7 to 24 gigahertz. Wow, it's difficult to HBT because HBT is traditional serial phone power amplifier. But for high frequency, high efficiency, the GaN nitride maybe is another solution. And Intel, IMEC, and CEA they also have some solution try to focus on this kind of applications. Okay. And for example, WebTech, we have the gallium arsenide HBT and the PHEM business for sure. And now we also provided RF GaN for the base station. We have the power GaN for the 650 volt application. So I mean, in Taiwan supply chain, if you want to earn the money, maybe the feeder will be the power electronics. But for the niche and high profitable application, how about to leverage the RF business into your fab? Okay, so this is the last page because I need a little bit time delay. And okay, you can read a sentence, but I just want to say where to play, who to play with, how to win. In Taiwan, where to play? Of course, you need to focus on the niche market, high technology barrier compared to the rate supply chain, and you have to find the correct business for Taiwan. And who to play with? Yes, high reference customer or high technology background customer to support you because they have to give you the correct system level parameter for the foundry side. How to win? You have to find the good technology. You have your own technology to solve the different kind of the power electronics or application weak point and try to solve the solution compared to the IDM supply chain. So that's my talk. Hope my presentation can help you to create a closed loop Taiwan ecosystem. Thank you.